So Samson Hagos is going to present on the application of machine learning to understanding and parameterization of cumulus convection. And so if you're not presenting, I'll ask everyone to basically turn your video off until it is your turn. I would do the same. Go ahead, Samson.
Thank you, Joe. Thank you, everyone. This work is done at PNNL with help from Jingyi, Koichi, Zefeng, Heng Xiago, and Bob Plant at University of Reading. The problem that we are trying to address here is a very familiar one in the convection community. That is, how do you represent a population of convection dynamics like this? This is radar observations in Northern Australia at Darwin. So the general conceptual model that had been used to represent convection in climate models is that based on Arakawa and Schubert. And the main idea is you have forcing that initiates convection, and the convection results in mass flux that sort of dumps or responds to that forcing. So the imbalance between the forcing and the mass flux is what's driving the population dynamics. Now, in climate models, the general approach has been to assume quasi-equilibrium, that is, the mass flux effectively balances the forcing instantaneously. What that means, if you consider, for example, convection over land, is then if you have forcing that peaks at noon, then convection also peaks at noon. And that's a problem. That's what we see here in, say, CMIP5 models. So how do we deal with this problem? Now we come up with a different conceptual model that looks at the evolution of the population dynamics. Suppose that the forcing says the convective area over a certain area box should increase by some DAC. Then that means you have a piece of a cloud that has to be added to this box, but you wouldn't know where it would end up. So it could end up here, making a large cloud larger. It could end up here, or it could form a new cloud. So how do you decide this determines the evolution or the population dynamics of the cloud? Now, so you could formulate it like this, the FC being the transition function that determines where this cloud will land. Now, you could assume a simple case where you say there is no preference, the probability distribution is uniform. Then if you do that, then you get something like this. You get a lot of small clouds, and that's inconsistent with CPM simulations or the CPOL radar. So what that means is there is organization, that is, clouds tend to form in the vicinity of clouds, as you would expect, because the clouds have formed already for that same reason. Now, you could modify this. You could say, well, there is preference for clouds to form in the vicinity of other clouds. Then you could choose a parameter that gets you agreement with observations. So that in that sense, that empty space is less favored than a vicinity of clouds. So you could do that. And then when you do that, then you could correct the Darner cycle. That is, with time, as the day goes on, you start out with small clouds far apart. Then as the convective area increases, there is a delay, but the convection peaks later in the afternoon. The mean size, cell size increases. So that tells you that organization plays a role in that delay in the afternoon convection. Then you can go even further. You could say, well, what about the interaction among clouds? Then you could generalize and develop a machine learning assisted model. We call this LAMP, learning assisted model for parameterization. The idea is you take a 1 kilometer grid spacing simulation and you make grids of 25 kilometers square, for example, in this case, and get the size distribution represented by C, cell size distribution, and its evolution. Then you train an algorithm with that data. But your goal is to get that FC. Now you have the true change in cell size distribution, and you try to correct that predicted, and you get your weights, and hence your optimized function. So we use, in this case, a single hidden layer with ReLU activation function. We try to keep things as simple as they can be. So this way you can represent the organization. That is a small convective area fraction. You see this sort of randomly distributed mass flux on the left hand side, and as you increase convective area, you get organization that is strong mass flux at a specific range of mass flux bins. So that's what you want to capture in the evolution of convection with change in convective area. Then we couple this with WRF. So the idea here is we get closure, that is, we assume that the convective area fraction is proportional to the resolved mass flux, cloud-based mass flux. Then you get a change in convective area fraction. Then the cloud population model produces a size distribution of the cells. It advances forward. So you have a spectrum of convective cells with their own cloud-based mass flux. You feed it to in-training plume model, which does its very simplified microphysics. And then you get the moistening tendency, heating tendency, and precipitation. So that's how we couple the cloud population model with WRF. So for closure, as I said, the resolved mass flux is used as an estimate of the convective area fraction. And we require, of course, that the Cumulus parameterization shuts off itself smoothly at 1 kilometer grid spacing. So it should work smoothly between 25 kilometer and 1 kilometer, shifting the mass flux, as you see here, gradually to the 1 kilometer grid spacing. So in that sense, it is scale aware. So that brings us to say, for example, we can look at a diurnal cycle of convection and many other criteria that we look at to evaluate the model performance. So this non-equilibrium approach gives us a better representation of the diurnal cycle as we expected from theory. And the next step is to look at the sort of get process level understanding between convection and stratiform, convective and stratiform clouds. To do that, we use 12 winters of CPOL radar reflectivity data, 10 with 10-minute increment. So once you have a snapshot like this, you can use Steiner et al. Algorithm to separate convective cell distribution, which is represented by CT as a vector here, and the stratiform area, which is assumed to be a scalar. Now, in order to understand the interaction, we need a model. So the model looks like this. The first equation is the one that I just described, sort of originally from Arakawa and Schubert. So the problem at hand is now, given a previous state, how does the cell size distribution represented by vector C evolve? So it's assumed to be a function of the previous time step convective cell size distribution and the stratiform area and the change in total convective area fraction, which comes from the closure. And the stratiform area is assumed to be a decaying function of the current stratiform area and also the production by the convection, which is represented by Fs. So the goal of the machine learning algorithm, therefore, is to determine this to Fc and Fs to provide closure to this model. So we, again, put together a machine learning algorithm. We have initial state S sub t and C sub t as a scalar and vector representation of stratiform and convective area, respectively. You have the change in convective area fraction. You have true change in convective area, and you have a ReLU activation function, a single hidden layer machine learning algorithm to optimize FC, and the same for the stratiform area as well. So we have a lot of data that have been collected over many years. So we were able to train and test this model. So of course, we look at how the cell size distribution relates to convective area both in the CPOL and in the LAMP model that I just described. So once you are satisfied with this, then you can ask questions like, what is algorithm learning and what are we learning? So if you look at the convective area fraction in the horizontal and convective cell size in the vertical, you can look at the growth rate of stratiform area. So of course, if you have large convective area fraction, you get larger growth rate of stratiform area, which is fine. But if you look at the change with respect to convective cell size, it actually decreases. What it is saying is that stratiform area growth increases with convective area, but decreases with convective cell size average. That is, for the same convective area, the smaller, larger number of cloud convective cells would produce more stratiform area than a larger, fewer clouds. So what does this mean? So we can look at the theory. The theory is that you have, for example, convection as represented a particle fountain. So what that means is the amount of material hydrometeors coming out of the convection would be proportional to the perimeter of the convective cells. Therefore, the more cells you have, the larger perimeter you have for the same area. Therefore, the ratio of stratiform area to convective area goes as R by C. That one can do this kind of calculation on the back of an envelope. Then you can validate that by just calculating this ratio and the function of mean convective cell size, and that's approximately what you get. So what this machine learning algorithm is telling us is that the theory in fact is adequate to represent this relationship between convective and stratiform area. So therefore you are justified in terms of getting parameters from these kinds of models in developing a model for population dynamics of clouds. So in summary, what this kind of work tells us is that we could use machine learning judiciously by first identifying the process that we fully understand, and then process that we want to understand, and also process that we may want to understand but are not key at the moment, that we could use a machine learning algorithm for parameters and for closure. So once you have a physics-based model and a hypothesis, then the machine learning algorithm could assist us to test whether our hypothesis is correct. And if the hypothesis is correct, then what parameters would be provided for the closure. If the parameters and the closures do not make any physical sense, then we have to go back and check our hypothesis, or otherwise you would have the structural problems that we just have been discussing. So I just want to acknowledge the support of the ASR program and the iClass SFA in supporting this work, and the ARM Climate Research Facility for providing the long-term CPOL radar data that we use to analyze and train our machine learning algorithm. Thank you.
So questions, and while we wait for questions to come in, I had one. So have you run this online at all? Or because I know you showed coupling with WRF and everything.
Yes, we run WRF. It's coupled. We have a version of WRF that has LAMP as an option for Cumulus parameterization.
Nice, that's really cool. Okay, well, while we found one, so have you looked at? So you were doing some exploratory analysis, like what is learned. Have you considered looking like the individual weights and like what incoming parameters it's weighting to try and look at the function it's actually learning? Since you have a pretty shallow network, right?
It's a little tricky, as you may know, because you have that nonlinear relationship in the activation function, but you can produce an array, a sort of Markovian transition function, and look at the diagonal elements and off diagonal elements to understand what the sort of the weights associated with interaction among clouds versus the cloud doing its own life cycle and so on.
Okay, and then we have one question in chat. Would this work in a coarse resolution GCM?
Yes, well, we are running it at 25 kilometer, but there is no reason to not coarsen it if one chooses. Again, that closure that I showed, that smooth transition between 25 and 1 kilometer, you can extend it backward. But the key here is the range between 25 and 1 kilometer is narrow enough that the closure, the resolved closure, sort of gives a first guess of the cloud-based mass flux. But if you go to much coarser resolution, that assumption might be questionable.